this video, we'll talk about partial derivatives. So let's give the definition. Let's say that A is a subset of R, let's see, N, and let F be a map from A into the real numbers, so a real valued function. For J from 1 to N, we define the jth partial derivative of f at the point A. So A is an element of A. Now here I may or may not write the arrow above the A. I mean, here it's clear that we're talking about an element of A. So the partial derivative of f at A to be the directional derivative of f at A with respect to the vector Ej, provided this derivative exists. And we denote it by partial f partial xj evaluated at A. Okay, so here I'm writing the arrow. I may or may not write it. So in other words, this is saying that partial f partial xj evaluated at A is defined to be the limit as t goes to 0 of f of A plus tej minus f of A all over t if it exists. Okay? So let's just look at an example. Let's just look at f of x comma y equals x squared y. So this is going to have two partial derivatives, partial f partial x and partial f partial y. Let's look at partial f partial x. This by definition is, so at the point a1 comma a2, right, when you evaluate it at a1 comma a2, this is equal to, by definition, the limit as t goes to 0 of f of A plus te1 minus f of A over t. Well, what's A plus te1? Right? This is a1, a2 plus t1, 0, and that's a1 plus t, 0. No. It's, okay, I'm running out of space. This is a1 plus t, a2. Right? So this is the limit as t goes to 0 of f of a1 plus t comma a2 minus f of a1 a2 over t. And this, by definition of f, is the limit as t goes to 0 of a1 plus t squared times a2 minus a1 squared a2 over t. And we can pull out the a2 in front, so it's a2 times the limit as t goes to 0 of a1 plus t squared minus a1 squared over t. And this ends up being, okay, let's see, a2 times the limit as t goes to 0. So you distribute, you get 2a1t plus t squared over t. You cancel out the t, so this is the limit as t goes to 0 of 2a1 plus t, which is equal to 2a1, so the final answer is 2a1a2. So notice that the partial derivative, so that's what the partial derivative of f with respect to x is. It's a function of two variables. If f is a function of two variables, then partial f partial x is also a function of two variables. And when you plug in a1, a2, you get 2a1, a2. Now notice when you look at this expression, this, okay, so when you look at where t is, it's in the a1 part, and this function is what you get. Notice that in this part, a2 is the same second value as this one. So the only difference in the numerator, right, is that you have an a1 plus t in the first term and then a1 in the second term. So what we can say is, if we define, so note that if you define a function phi of t to be f of t comma a2, then the partial derivative, partial f, partial x, evaluated a1, a2, is just phi prime of a1. Right? This is just definition of the limit. I mean, sorry, not the definition of the limit. Definition of the derivative of a function of one variable. Right? You just keep a2 constant, and this is a function of a1. Yeah. And so let's just take a look at partial f partial y. So if we look at partial f partial y, this is by definition. See, so what we can do is, instead of writing out this limit definition, we can just substitute. So to figure out partial f partial y evaluated at a1, a2, we substitute a1. So we look at f of a1y, or f of a1t, is a1 squared times t. And now, so this is phi of t, and then you take phi prime of t, that's equal to a1 squared. And so phi prime of a2 is just a1 squared. Okay, so let's just write out in general what's going on. So in general, partial derivatives so partial f partial y evaluated at a1, a2 is a1 squared. The partial derivatives are usually easy to calculate if a equals a1 through an. Okay, then define phi of t to be what you get when you substitute everything except the jth term into f. So you get a function of one variable. Then the jth partial derivative of f at a equals the ordinary derivative of the function phi at the point t equals aj. In other words, partial f partial xj can be evaluated by, or I should say calculated, it's probably more precise, can be calculated by treating all the xi's except for xj as constant and differentiating the resulting function with respect to xj. So let's just do an example. Let's say that f of xy is x squared y plus cosine x plus y. So then partial f partial x, so you keep y as constant, so this x squared y, so if it helps, it just, you can pretend that y is like 5 or something and see what you get. So it'll be 2xy, and then minus sine of x plus y, and then there's a chain rule, there's a 1 plus 0. And partial f partial y is going to be, so now you keep x constant, so you pretend x is 5, say, so you get 25y, okay, so you're going to get x squared, and then minus sine of x plus y again. Okay, let's take a look at a more complicated function. So let's say that you had f of xy equals 3x squared y minus y cubed over x squared plus y squared, if x and y, if x comma y is not 0, 0, and 0 if xy equals 0, 0. So how do we figure out partial f, partial x, and partial f, partial y? Well, we can say what happens if a1, a2 is not 0, 0, so we have partial f, partial x equals, we can just use the top function, because that's what f of xy is everywhere except the origin. So we keep y constant, right? And we have to use the quotient rule. So it's the bottom, so it's x squared plus y squared, times the derivative of the top. So we get 6xy, and then minus 0, because we're treating y as constant. Then minus the top, times the derivative of the bottom, that'll just be 2x, all over the bottom squared. And this simplifies to 6x cubed y plus 6xy cubed minus 6x cubed y plus 2xy cubed on the top over the bottom squared, and the 6x cubed y's cancel, so, and then you can add the two terms together and get 8xy cubed over x squared plus y squared squared. So then if a1, a2 is not the 0 vector, then partial f, partial x evaluated at a1, a2 is 8a1, a2 cubed over a1 squared plus a2 squared in parentheses squared. And let's just do partial f, partial y. So this is going to be okay. Well, why don't you give it a try and then we'll check the answer. Okay, so you use the quotient rule, so it's the bottom times the derivative of the top. Now we're keeping x constant, so we're going to get 3x squared, and then minus 3y squared, and then minus the top, 3x squared y minus y cubed, and then times 2y over the bottom squared. Okay, now the algebra gets a bit more complicated. You get 3x to the fourth minus 3x squared y squared plus 3x squared y squared minus 3y to the fourth minus 6x squared y squared plus 2y to the fourth all over the bottom. And then, okay, these cancel, so you're going to get 3x to the fourth minus 6x squared y squared, and then the minus 3 to the y fourth plus 2y to the fourth makes minus y to the fourth over the bottom squared. That's partial f, partial y. If x comma y is not 0, 0. So therefore partial f, partial y evaluated at a1, a2, as long as a1, a2 isn't 0, 0, is 3 times a1 to the fourth power minus 6 a1 squared, a2 squared minus a2 to the fourth power over a1 squared plus a2 squared parentheses squared. Now what happens if a1, a2 is 0, 0? Well, if you look back at the definition of the partial derivative, Okay. What you're really doing when you're taking the jth partial derivative is you're setting all the other x's equal to the ai's, and then you're differentiating that resulting function of one variable. So in this case, we can just plug in, so to figure out partial f partial x evaluated at 0, 0, we can substitute y equals 0 into f of xy, and that will give us, okay, what will that give us? So if you substitute 0 in for y, this is going to be 0, that's going to be 0, that's going to be 0. So you just get 0 if x is not 0, and 0 if x is equal to 0, and so you just get f of x comma 0 equals 0. And now we take the derivative of this with respect to x, right, and then plug in 0. So let's call this phi of x, and now phi prime of 0 is just 0. So partial f partial x evaluated at 0, 0 is 0. Now what about partial f partial y? So to find partial f partial y at 0, 0, substitute x equals 0 into f of xy. So what we get is a function of one variable, which is, okay, so if you substitute x equals 0 in here, you're going to get 0 here, and 0, ooh, wow, no. Okay, that was unintentional. Oh, I have to be careful with this. Anyway, if I substitute 0 in for x, then I get negative y cubed on the top and then y squared on the bottom if y is not 0. So I get negative y if y is not 0, and 0 if y equals 0. Well, that function is just, right, that's just negative y. And so the partial derivative with respect to y at 0, 0 is just phi prime of 0, which is negative 1. Okay? So those are some examples of partial derivatives. And we'll use partial derivatives to get a criterion for the differentiability of a function, and we'll see how partial derivatives are related to the determinant of a function of several variables. We talked before about the derivative of a function, of a differentiable function from Rn to Rm. The derivative or differential is a m by n matrix, and we will see that the matrix can be described in terms of the partial derivatives of f. Well, the partial derivatives of the component functions of f. Okay, thanks.